Hi everyone, welcome, and the quantum computers are coming. I'll be taking questions at the end of the talk, so if anything comes up, try to remember it. So, who am I? My name's Alasdair Collinson. I'm a software developer for Xenocor Technologies, and blah, blah, blah. You don't really care about any of that, do you? There's really not much you have to know about me, but one thing you really do have to know is I'm a nerd. In fact, I'm so much of a nerd that my colleagues call me a nerd. One of the main contenders is sitting over there. And the colleagues that call me a nerd are, other computer scientists and mathematicians and physicists. Now, personally, I'm not a physicist, not in any stretch of the word. Yet, I'm here today to talk about quantum computers. The thing is, we are getting to a point where you don't have to be a physicist anymore. Being a nerd is quite sufficient to start working with quantum computers. And that's what we're going to do today. So, first of all, what is a quantum computer? Two parts to the term. Let's start with the easier one. What's a computer? Well, this is a computer. Rather older than what most of you are probably used to, but this is a replica of the Zuse Z3, arguably one of the first computers out there. It was certainly the first digital programmable electronic computer. And the digital or binary part of that is really important because basically mostly everything that came after it was binary. Now, when we say binary, normally we think about zeros and ones, but that's not really correct if you get to the base of it, is it? Basically, all we need is two distinct values, and for what we care, that could be, a green circle and a red triangle. Just have to be distinct. Now, computers that we use in our everyday life and work are based on transistors, much smaller than the ones depicted here, but same principle. The principle being that depending on the input the transistor gets, it either lets a current go through or it doesn't. And this is great for many, many problems. You can solve so much with this attempt. I mean, just look at what we've managed over the last few decades. But it's not perfect for everything. And I'm going to give you an example for something that it's not so great at, with something that you, as people who are visiting a talk on quantum computing in the afternoon, you're probably nerds, so chances are you may be familiar with it. Nature. So nature is really difficult. Nature is non-binary. What do I mean with that? Well, where in this image do we have forest? Let's just look at a small part of it. Here, this part, that's certainly forest, right? And this part certainly isn't forest. But what about this area here? I mean, there are certainly trees there, but most of it is grassland. So where do we draw the line? And that question, where do we draw the line, means that we have to make a decision. We have to decide so many trees per, square kilometer or whatever, means it's a forest, and anything beneath that means it isn't. And that's an arbitrary line we are drawing. We are artificially making it binary. And that's where the second part of the term quantum computing comes in, quantum mechanics. Quantum mechanics was first thought up by Nicholas Bohr and Werner Heisenberg in the 1920s, and they worked together, Heisenberg being Bohr's assistant for quite a while in Copenhagen. In Copenhagen, they came up with the basics of quantum mechanics and what became known as the Copenhagen interpretation of quantum mechanics. I don't want to go too deeply into the material, not least because, as I said, I'm not a physicist, so I'll go with an example. The example is, let's imagine we have an atom. This is a radioactive atom. We don't care about the whole atom. In fact, we only care about the nucleus. Okay, I said this is radioactive. What does that mean? That means that at some point it will decay, which means part of the nucleus splits off, and this particle, alpha particle in this case, is emitted. So, assuming you start out with a full nucleus, after a time you measure the state of that nucleus, and there's two possible situations that you could get. You could measure that nothing changed at all, or maybe it decayed. And according to the Copenhagen interpretation of quantum mechanics, you can have both of those states at the same time. They overlap. That is, until you measure, and then it decides. Now, I want to be very clear here. Measurement does not necessarily mean human intervention. Measurement is anything that depends on the state. So we're not adding consciousness to physics here. But nevertheless, it is rather weird to think something could be in two states at the same time. And we're not the first people to think that. In fact, one great mind who also thought that was this guy here, Erwin Schrödinger. And Schrödinger came up with a thought experiment which showed just how absurd this notion was. The experiment, quite a few of you have probably heard about it. It's Schrödinger's cat. So let's go through Schrödinger's cat experiment just very briefly. We have our cat, and we could put the cat into a box. Now, also in this box are a few other items, namely some radioactive mass. Now, this mass was chosen very specifically so that within an hour, if you measure after an hour, the chance that you would measure any decay at all is 50-50. Okay, so we have that mass. What else? We have a flask with cyanide gas. Cyanide gas is, of course, rather poisonous, so it's better if that gas stayed in the flask. And last but not least, we have a Geiger counter with an attached hammer. So what happens if the Geiger counter were to detect any radiation? Dead cat. Okay, so according to what we did just now, if you measure after 1 hour, there are two states which you could measure. One in which the radioactive material has not decayed, so everything's fine, and one with a dead cat. And if you believe in the Copenhagen interpretation, you get both of those states. You get them at the same time. They're overlapping. So our cat is dead and alive. So what's dead and alive at the same time? Schrödinger wasn't thinking of zombie cats in this case. Instead, he came up with another interpretation of quantum mechanics, because he did think that quantum mechanics was correct. Just the way people were thinking about it was nonsense. What he came up with became known as the many worlds theory. And this states that you take everything there is, the world, the galaxy, the universe. I couldn't find a picture of the universe, but let's take the galaxy here. And in that galaxy, you have, among other things, your cat. Now, when such a radioactive event happens, so a situation in which the radioactive material may or may not decay, or at least that would be what your measurement would show, rather than getting that weird zombie cat here, what happens instead is this. The universe copies itself with everything exactly the same except for the result of that quantum event and everything that followed from it. So here you have two universes, one with a live cat, one with a dead cat. And of course this can happen again, giving you 4 cats, and again, you get a picture. Now, one thing you might notice in this image here is we have rather many dead cats. And that's a problem for any cat lovers, of course. And it's also due to the fact that biology just works that way. I mean, if you have a cat, a dead cat, and add more cyanide, you won't get a live cat. Biology just doesn't work that way. Luckily, qubits are not cats. And qubits are what are important to us in quantum computing. So now we're bringing the two topics together. What is a qubit? A qubit is the analog of a regular bit, you know, those things with distinct states, two distinct states in our regular computers. And qubits too can have the value 0, which would look a bit like this. In the representation I've chosen here, that's called a Bloch sphere, by the way. So a vector pointing straight up, or it could be 1, which is a vector pointing straight down. So far so good, but it can also be somewhere else on this sphere. So suddenly we have so many more values available that could be present at any time. And actually this vector here is a combination of 0 and 1 state. Now, if you find the maths here confusing because, you know, 0's at the top, 1's at the bottom, and you add them up and you end somewhere else, this is a 3-dimensional representation of 4-dimensional vector space. Math gets weird. If the math confuses you, just ignore it. We don't need it for this talk. Now, like with any binary computer, or generally binary electronics, we can use certain gates to modify our qubits. So the first one I want to talk about is the Hadamard gate. If we have our qubit, in this case in 0 state, and we apply the Hadamard gate, it imagines that there's a further axis between the x and the z axes, and then spins our vector around that axis. If you were to measure the value of the qubit in this state, you would get 0 and 1 with equal probability. So you would get 0 one time you measure, and 1 the another time you measure. This is what's called quantum superposition, and it's going to be really, really important later on, so try to remember that. Not everything is quite as exciting, though. I mean, you do get, for example, the Pauli X gate, which, assuming, again, the same starting position at 0, if you apply that, it just takes the x-axis and spins our vector around there, which basically makes this a kind of NOT gate around the x-axis. That's comparatively simple to imagine. It gets exciting when you combine this X gate with a condition, and that's called the conditional NOT, or the C-NOT. Now this is a 2-qubit quantum gate, and let's imagine that this gate here is our measure gate, our control gate. So the idea is, if that is at 0, and we apply the C-NOT gate, then nothing happens to the second gate, which we'll call the target. If it's at 1, our control gate's at 1, and we apply the C-NOT, then we'll get the effect we got with the X gate. So far, so good, but what happens in this case? What happens if our control gate is in superposition? And what happens is basically this. Suddenly we have 2 arrows there. And it's maybe a bit easier to imagine if what we write, or what we show, is this here. So basically we have the control gate and the target gate locked together. They're entangled. This is the situation we had with Schrödinger's cat and the radioactive isotope earlier. They're either both 0 or they're both 1. You don't get any states where they're mixed up any other way. This is called quantum entanglement. This is the other huge concept that quantum computing brings to the table. Now, it doesn't actually look like this. In fact, it's closer to this because we haven't measured at any point. The control gate isn't measured in the sense of us looking or any other physical process requiring it that isn't quantum in nature itself. So we do have an overlapping state. We do have superposition in both qubits now. Okay, so that's very theoretical. We'll get to some actual applications very soon. Just to finish this part, I've shown you the Hadamard and the CNOT gates. I've shown you one of the three Pauli gates, the X gate. The Y and Z gates are pretty much the same. They just spin around different axes. I didn't show you the identity gate, which is extremely boring because it simply does nothing. I didn't show you any phase gates, which are much more exciting but too complicated for this kind of talk. And there are many, many others you could imagine. But why do you want this kind of stuff in the first place? What are the use cases for, that kind of logic, which seems rather abstract and weird? Well, there's quite a lot you can do with it, in theory at least. So one thing you probably heard about, if you've heard anything about quantum computing, is it can potentially break encryptions. But it can also be used in what most people would consider more constructive ways. For example, it can help construct cars, design cars. It can be used to simulate molecules for chemical and medical research. It can be used in AI, potentially, and have huge effects there. It could be used for weather predictions, or financial fraud analysis, or NASA uses it for engineering. They have a very, very early quantum computer in use right now. I don't think they have it in productive use right now. It's still in the experimental phase, but it's going to get there. And to go with a trend, it can break Bitcoin. So if you've invested Bitcoins, you should probably get rid of them before quantum computers hit the big market. Now, quantum computers are great for many, many subjects, but they're not strictly better than our binary computers. For example, for simple arithmetics, quantum computers suck. They'll give you answers that may be correct with a certain probability. So that's not what you want. Quantum computers can make a lot of things faster, but they won't replace regular computers. They'll add to them. Basically, it's always a case of choosing the right tool for the job. I mean, going back to what we had earlier, if you have a flask of cyanide and you want to break it, if you have a hammer, that's a great solution. Break the cyanide with a hammer. Not a good idea in general, but that's a good solution to fulfill your objective. If, however, you have a cat and try to break the flask with the cat, it's gotta get weird. So better not try that. Finding problems that can be solved with quantum computers easily is a big task that we'll be facing in the next years and decades. People have been working on it for quite a while, at least since the 1980s, but there's still a lot more work to do. And most of the work that's been done so far is rather theoretical and academic. We need real-life computer scientists, programmers, people who work in the field to work on this topic. Basically, we need you to join the cause. Why should you do it, though? Well, here's a very nice quote by Venkat. Basically, he says, if you want to learn something, try to learn something that's just totally different from what you've known so far. It'll help you immensely. And believe me, quantum computing is different from any kind of programming you've done so far. And you can actually start programming a quantum computer right now after this talk. Not during the talk, well, you could, but I'd recommend you don't. And I'm going to show you two ways that you can actually do that. So the first way is via the IBM Quantum Experience. IBM offers a quantum computer in a cloud, so to speak. And they've built several quantum computers by now. The quantum computer is in here. Now, what you see here is not the actual quantum computer. That's a cryostat, a kind of huge freezer. The quantum computer itself looks a bit like this. This is actually a 7-qubit quantum computer, which IBM built. And the way that this particular quantum computer works, and quite a few others, though there are other technologies available, is via superconductors, so it has to be cooled to close to absolute zero. We'll actually see later the kind of temperatures they reach. They don't reach absolute zero because, as far as I know, nobody's been able to manage that yet, but they get pretty close. So I said this is in the cloud. Basically, the easiest way to get started with it is via their website, and you can log in to that. They have great, you see it down there, the beginner's guide. They have great information. If you register and log in, you'll see something like this. This is the composer view. Up here, we see information on the state of the qubits they're offering for us. So you can write code and run it on their quantum computers. I want to emphasize that again. And here's a bit of information on the state of the 2 qubits you can choose from in this case. They do have, for their partners, a 20-qubit computer available as well, by the way. It's not limited to 5 qubits like these two examples show. And this here is the most important part. This is the actual composer part, named so, of course, because it reminds you of musical notes, and what you write in there is called a quantum score, as you can see at the bottom, where it lists the quantum scores that I've produced and haven't deleted. Also on the side, you see the various gates that you can use, and you'll recognize a few of those from what I've shown you earlier. Now, let's build a kind of quantum Hello World program with this. And the Hello World program is what we've already seen, Schrödinger's cat. So, what do we need? We need our radioactive material. We need our Geiger counter with the attached hammer. We need the cyanide, and we'll already have the cat there. And all of those have to be linked or entangled. So if we build this in the quantum experience, it would look something like this. So the radioactive material here is a qubit to which we have applied the Hadamard gate. We've put it into quantum superposition, so it's in both states at the same time, that kind of stuff. We link another qubit which represents the Geiger counter to that via a CNOT gate, and to that we link another qubit which represents the cyanide, and another qubit to that which represents the life of the cat. And looking into the box is represented by this pink icon here, the measurement gate. Actually, let's not just measure the life of the cat, but let's measure all of those qubits there, so we can get some interesting information, more detailed information. And if we run this algorithm on the quantum computer, the result will look something like this. So what do we have here? How do you interpret this? This here is the case where everything's fine. The radioactive material did not decay. The cat's alive. No one has to worry. And this occurred in about 30% of the cases. This here is the case where the radioactive material decayed. The cat is dead. All is lost. But we do have a lot in the middle here. And that, what you see here, those are mistakes. The quantum computer is still an early prototype, and quantum error correction is a huge issue right now. all in all, we got 60% of the results in areas that seemed reasonable, and round about 40% that was errors. So that's a huge margin there. There's a lot of work to do, but it's being done. I'll show you an example of a chip later that apparently at least has a much lower error rate. So things are getting better, and they're moving fast. Okay, so this is the first. One thing I should mention. This was purely graphical. There is a way to use the quantum computer or the quantum computers IBM is offering via a programming interface. They offer something called QIS Kit, which, among other things, offers you a Python interface to send code to that computer. I'm not going to go into any detail about that, but if you're interested, you can. The second project I want to show you is the Microsoft Quantum Development Kit. This came out about half a year ago, and this is much closer to what we know as code from our everyday life as developers. Now, since this is Microsoft, they initially released it for Windows, of course, and while preparing this talk, I thought I would have to tell you, well, if you don't have Windows available, tough luck. And then about 2.5 weeks ago, they tweeted out, yay, it's available for macOS and Linux as well now. So, time to party. Let's have a look at the very same algorithm we programmed on the Quantum Experience in the language Microsoft is offering called Q#. So, this is a really, really simple program we have here. First of all, most of this is blurred out on purpose. What's important right now are these 4 lines that aren't blurred out. First of all, we put our qubit into superposition via the Hadamard gate. So this is our radioactive isotope. Then we link it to the Geiger counter. We link that to the cyanide, and we link that to the cat. So 4 lines of code, and we've built basically our experiment. Everything around it is, well, kind of boilerplate, really. But we'll go through it nevertheless, most of it at least. What we have here is we need some variable that tells us what the current state is, what the value is we should return. Now this, as you can see, is just a regular variable. It's a mutable variable. Most things in Q# are immutable. You have to specifically state that you want to be able to change the value of something. Here we look into the box. We check, has the cat survived or not, and assign that value to our variable, and then we return it like we would with any other function. Is our cat alive or not? And a bit more boilerplate. First of all, we have to tell it that we want to use 4 qubits for this experiment. This is a bit like a malloc in C. We have to reserve our qubits. And then we have to, well, we don't have to, but I chose to give them helpful names because in qubit 0 through qubit 4, that's not that easy to understand as soon as your program gets even a little bit larger. So let's give them names. These, as you see, are not noted as mutable, so those are immutable in the sense that the references are immutable. The qubits themselves are mutable. That's why we have to set them back to 0 at the beginning. We don't know what we got initially. We want to make sure that right at the beginning we start with a known state. So 0 is our best bet, which is, by the way, something that the Quantum Experience did automatically for us. We didn't have to do that manually. And after we've finished, we have to make sure it's cleaned up again. This is a requirement by the language. We have to clean up behind ourselves. And that's basically it. This is our Q# code. And Q# implies that it may be related to some other languages. It is in fact a .NET language, and so you can use it throughout the .NET platform, which means here we'll call it from C# code. So first of all, let's create a quantum simulator. Unlike IBM, Microsoft is not offering an actual quantum computer that you can use. They're offering a simulator. That makes development locally much faster, because with the Quantum Experience, you have to send them your code, wait until it's your turn, and then you'll get your results back. Here, you just run it locally. Then we run our experiment. We just call our Schrodinger's cat code, and then we check the result and give outputs depending on that result. And that's it. We've written a quantum algorithm which you can run locally on your computer. Now, this is using a quantum simulator, which kind of begs the question, why don't we just use quantum simulators for all of it? Why do we have to build real quantum computers? Why not simulate everything? And to answer that question, I'd like to go back to a previous slide. Remember this slide here? Now, when I press my clicker in a moment, what we should get, in theory, is a really smooth transition to the gravestones. Yeah? That wasn't smooth at all. My computer is having problems with PowerPoint. A quantum computer is rather more complicated than PowerPoint. And if you want to, if you're wondering how much more complicated, well, IBM actually looked into this. There's something around called quantum supremacy. It's a concept. Basically, it means the point at which we can build and run a quantum computer which can do things that a regular computer cannot, at least not in any reasonable amount of time. And so what they did is they decided we'll simulate a rather large quantum computer, actually two of them, on their supercomputer. And so the first one was a 49-qubit simulated quantum computer, and that needed 4.5 terabytes of RAM. The other one was a 56-qubit, and that needed a little less, though I should note that this wasn't the same experiment. They ran something different on the 56-qubit computer. So it's not like the more, the better. But what's really astounding is this is a huge improvement compared to other state-of-the-art technologies. With anything that came previously, you have rather larger amounts of memory you need. 8 petabytes or 1 exabyte. Let me repeat that. An exabyte. Can anyone imagine how large an exabyte is? Let me break it down for you. 1 exabyte, that's 1,000 petabytes. That's 1,000,000 terabytes. Depending on whether you speak British or American English, that's a milliard or a billion gigabytes. That's 10 to the 18 bytes. 10 to the 18, what's 10 to the 18? According to current estimates, our universe is 13.7 times 10 to the 9 years old, which translates to 4.32 times 10 to the 17 seconds. That's less than half the amount of bytes in an exabyte. That's a huge amount of RAM. And even with the improvements, which don't necessarily work for all algorithms you run on them, that's pretty hefty. Now, you can run quantum simulators on supercomputers, but most of us don't have supercomputers just standing around in their basements. So for the time being, we're probably bound to something like this. And this is actually a 50-qubit quantum computer that IBM built. They're not offering that on the Quantum Experience, at least not at this time. And until very, very recently, I thought this would be the largest quantum computer I would be able to show you today. until literally a week ago, 7 days ago, Monday last week, Google said, hey, we have something here. We call this Bristlecone, and it's got 72 qubits. And apparently a very, very low error rate. Now, this isn't quite complete yet. This is still in testing. But 72 qubits, that's about 1.5 times the previously largest actual quantum computer with 50 qubits. This could actually be a contender to break quantum supremacy. Now, I don't know whether that's actually going to happen. That depends on quite a few questions, like how high or low is the actual error rate? What is the kind of algorithm you're going to run on there? And can you run an equivalent algorithm on a binary computer with, equal or better results? So it's open. We don't know what's going to happen. But this is pretty cool. And Google is just one of the contenders here. Intel is also working in the field. IBM, as I said, is working in the field. The NASA, I don't think they're building quantum computers. They're certainly using them. Alibaba is working with a university to build and offer quantum computers to their customers, and quite a few other companies. So there's quite a lot going on in this field. And I actually had to change the presentation about 3 times in the last few weeks because new things happened. Okay, so let's say I've convinced you. Let's say you want to get into quantum computing. What can you do? Well, there's a few things you can do. First of all, you could, of course, start using the Quantum Experience by IBM. It's completely free. It's really fascinating. It has great documentation. That's where I learned quite a bit about what I'm telling you today. You can also, of course, get the Quantum Development Kit from Microsoft, also totally free. And at least for the kind of experiment you'll probably be doing, you don't need multiple terabytes of RAM. In theory, you can also go to Alibaba. They announced on March 1st that they were offering an 11-qubit quantum computer on the Alibaba cloud. I registered and looked. I couldn't find it. I couldn't find anyone who had written about having found it. I've contacted their support and I'm still waiting for a reply. So probably it will be available pretty soon, but as far as I can tell, it's not quite available now. Also, some of you may have heard about this website, Stack Overflow. That's part of a larger network, the Stack Exchange network. And in what they call Area 51, they try out sites that they think may become larger. There's currently a proposal for a quantum computing site in that area. Now, this is a snapshot from last night, and we were at 56% commitment, which means basically we'd have just over half of the people we need to commit to do anything. I have it on rather good authority that there's going to be some kind of announcement very soon about this, and with very soon I mean later this evening or tomorrow morning. So you probably, if you find the field interesting, want to check that out. You can, scan that QR code and get right there, or Google it. That works perfectly fine as well. Apart from that, go forth, explore, try it out. It's really fascinating. I didn't get into even close to everything there is to say about quantum computers today. This was just, the very, very, very basics that you need to get started. But it's immensely fascinating. And estimations, including my own, say that probably within the next 5 to 7 or maybe 10 years, we'll have quantum computers basically in all major businesses. Things are speeding up right now. It could be earlier, especially if you're into security. You probably want to look into this very soon, because chances are organizations like the NSA and such will have quantum computers rather earlier than the rest of us. And there are ways to defend against quantum computing security attacks, but you really have to get into the topic. And other than that, I'm done with the presentation, and there's some time for questions. Yeah. There's a question back there, yes. Mm-hmm. Okay. So the question is basically, when you go from the quantum level to the macro level, you lose most of the quantum effect due to decoherence. And given that, and what is currently in the news and in this talk, obviously, about quantum computing, is it a hype? Do we actually have quantum computers, per se, that do anything interesting? We don't, at least if we leave out that Google chip, which I don't know enough about to say anything for certain. We don't have any problems right now that we can run on quantum computers faster than on real computers, on any quantum computer that we have at the moment. There are algorithms that have been proven to run faster on quantum computers in theory. We aren't there yet. So there are quantum computers, they're just in a very, very early stage. They're not in the stage where they're useful yet. It's going to happen pretty soon, I'm sure. Probably for most of us, it'll be a bit longer until they're useful. But the first applications for places like, NASA, that'll be within the next few years, I'm certain. Does that answer the question? Great. Yes. So basically, to recount the question, why am I so certain that quantum computers will be coming in such short notice? Basically, watching what's happening in the field and how things have sped up in the last couple of years is the main factor. The idea of quantum computers has been around at least since the 1980s. You could even argue it's been around since the 1950s in some ways. And for a long time, it has been very theoretical. In the last 1.5 to 2 years, things have really caught on. IBM is offering their quantum computer. They have a working quantum computer, which is limited, admittedly, but it's already a big step towards having something useful. Other companies, such as Intel and Alibaba and Google, have started building quantum computers that are getting so much faster, so much larger in such little time. Of course, there's the possibility, there's always the possibility that we'll hit a barrier in, 3 months' time and find out we can't build anything larger than those 72 qubits. That's possible. But right now, it's looking very good. There are problems to be solved, definitely. Before quantum computers can get to a state where they're truly useful, we probably need them in the sizes, several hundreds or maybe thousands of qubits for most interesting problems. And building quantum computers that have those many qubits that don't interfere with each other but can still be used together is a problem that, as far as I'm aware, has not been completely solved yet. So, sure, I might be wrong. The speed at which it's going right now does make me confident that we'll get quite a part of the way at least. If not there, we'll get quite a lot further within the next few years. I still believe that it will be a matter of 5 or maybe a few more years. But yeah, it's a valid question. I guess it's just belief in the end. Yeah. Okay, so the question is, why did I build the Schrodinger's cat example with 4 qubits when 1 would have been enough, basically? When you put 1 qubit into superposition, which would represent the isotope in my example, and measure that, you get 50-50 results. So that would be sufficient. It's just not very interesting. And also, I wanted to show the way that several different gates work together. And we heard the term decoherence earlier. The error rate is due to the qubits wanting to return to certain states. And that can be seen if you build the experiment like I did. I could have just built it with 1 qubit, measured that, shown you 50-50 approximately, and perfect world, you would have been none the wiser. The fact that we do get errors is really, really important. And anyone working with quantum computers in any fashion should be aware of those errors. So I made sure there would be sufficient errors to make the point. Any other questions? Okay. Oh, yeah, here. The question is, are there non-mathematical use cases for quantum computers? What would you define as a mathematical use case? Mm. Yeah, okay. So real-world applications, basically. There will be real-world applications, certainly. Right now, it's a field dominated by academics. And of course, academics mostly think of academic problems, which are in nature mathematical in many cases. There will be more interesting cases, I'm sure, but that's exactly why we have to get involved now. We who work in the real world, the business world, or whatever field you personally work in, there will be use cases far outside the examples I showed you earlier. We just have to find them. And there are some that go a bit above what we've seen, I mean, I showed an example of, or I showed that there was an example of modeling chemical and medical processes. Of course, you can break it down to math, essentially, but the idea here is that since we are working with nature, and nature is quantum, we should use quantum computers to model these things, because otherwise we have to artificially try to model these quantum effects, which we have in our quantum computers by default. And weather predictions, of course, weather is also, the models are also very, very mathematical, but they apply to something in the real world that right now we use heuristics for. Generally, many problems nowadays that we use heuristics for to optimize them, I assume can be solved in a better way with quantum computers sometime in the future. But in general, we just have to look for the problems. They're out there, I'm sure, but so far the right people haven't been looking. Anything else? Okay, I guess I'll release you to the beer, and thank you for listening.